Not at all, right? All right.
That's what they on campus. That's what campus
Went to this, Dr. Zell. You got to turn in 3 homework assignments.
So on the homework, guys, it is important. It's very important that you attempt the problems and not just leave them blank. Right? So whatever it is you try, put it down. Don't just leave it blank. Because if you leave it blank, I got nothing to work with.
Is chapter 9 really due tonight?
screwed up, but he said heads, tail.
No, the home.
No, he said
Yeah.
tail. Head.
Really, let's take 6 hours to do after you teach us.
I might think about it.
4.5 hours or something.
I'll think about it.
When I do this.
Okay? I'll think about it.
When I do it'll take me out.
That might be one class I might have got. Yeah. But there was one question that there was one part of chapter 6.
If you don't have a 0, you need to have it ready again. Okay? All right. Are you guys ready? Nobody wants to sit here anymore. Do I spit? Are you guys ready for the break?
Yes.
Yeah.
Let's start now.
We're talking about cool stuff today.
It's
Cool stuff. Mercury, Venus, Mars. Those are all cool. Eureka.
Here.
Michaela. Bren. Laurel.
Here.
Carly.
Here.
Kelly.
here.
Joe. Dakota. Here. Anna. Carrie.
Here.
Robert. Diamond.
Excuse me. No.
Marjwan. Dylan. Tanisha. Maisie. Justin.
Yeah.
Oh, Anna. Emily. Caitlin. Chelsea. Bailey. Bernicia. Shelby. Colton.
Here.
Tony. Colin. Stacy. Ryan. Chandretta. Stormy. Samantha. Casey. I wasn't very enthusiastic. Rolanda. Sheldon. Marquavius. And James. All right, so today we're talking about the inner. Got a question? Oh. All right, your name again.
Stacy.
Yep. All right. So, today we're talking about the inner planets. Mercury, Venus, Earth, Mars, right? They're all pretty cool. Why? Why they're all cool?
So they all had a unique way of doing things.
Because they're all solid.
They are the rocky planets, right? They're the ones that you could, stand on. Although, all right, it was daylight on Mercury, we'll get to that, but if it was daylight on Mercury, you'd burn up. If it was nighttime on Mercury, you'd freeze. And Venus, well, Venus rains sulfuric acid, so that wouldn't be very pleasant. Mars, yeah, no, Mars not bad. Mars is the one that's closest to what we're like. Who's going to go see the movie Martian? The Martian.
Great.
Yeah. Yeah, I hope you catch one. I do hope you catch one. That work? Right. That's an Epson. Samsung. That's not going to work. There we go. All right. So Mercury, Venus, Earth, Mars. These are the rocky inner planets. Right? All inside the asteroid belt. Not in your book or in this part. Ceres is a planet, a dwarf planet inside the asteroid belt. So we call these the terrestrial planets just because they're rocky like Earth is. Right? They're rocky like Earth. Both Mercury and Mars, well, Mercury is too small to have an atmosphere, and even if we're a bit bigger, being that close to the sun, it'd be kind of hard to maintain an atmosphere. Earth has a moon. Mars has two. Mars's moons are small, and they are asteroids that Mars happened to just capture. Remember, Mars is much closer to the asteroid belt than us, right? So Mars managed to grab onto a couple of asteroids at some point in the past. Okay. Mercury, small. And Mercury's surface is all kinds of craters, right? Mercury is not volcanically all that active anymore. It's cooled off, relatively speaking. Venus, a good bit bigger, right? These pictures are the same, or relative to size. Venus is a good bit bigger than Mercury. Venus has a very active surface in terms of volcanism. So Venus's surface is actually much younger than Earth's because it has a lot of volcanic activity going on. And a lot of lava flows and volcanoes, and, you know, in addition to that, Venus has a really dense atmosphere composed of sulfuric acid clouds and CO2, right? So we wouldn't last long there, basically. I remember when I was a kid, we sent a probe to Venus, and I may have told you this. One of the show and tell things they did was stick a construction hat outside the probe and film it dissolving away, just to give us a good feel for how bad it is on Venus. This is Mars and Earth with the sizes correct and relative to each other in the pictures. Mars has polar ice caps that are mostly CO2, but there's some water there. And then, you know, we have nice things like oceans and clouds and air that we can breathe. Mars has a thin atmosphere. Mars has also, because its atmosphere is thinner, more evidence of impact craters than we do, because both our tectonic shifts and our weather erode craters away. They don't do that on Mars so much. And then there's Olympus Mons, which we'll get to in a minute, which is an enormous volcano on Mars. It's now dormant, but it was an enormous volcano. Here are all the planets stuck together in a way we can see how the different sizes actually look. So Venus is very close to our size. The only problem with Venus is that it is too hot and acidic, right? Back before we really knew what Venus was made of, people said, oh, we'll go to Venus. Well, no, we're not going to Venus. But Mars is still very doable. I don't know about setting up shop and living on Mars. That's a different problem altogether. But, Venus is about our size. This, to give you a good idea of just how big our moon is, this is Mercury, that's our moon. Right? So our moon is relatively large compared to Mercury even. A lot of craters on Mercury and a lot of Maria on Mercury where there was a lot of lava at one point. You can see on Mercury, now, you might ask, where do we get these photos, right? We sent a probe to Mercury to go around it again and again and again and again, and eventually take pictures of all the surface of Mercury, right? That's where we have a lot of this data. And not only did it take pictures with standard light images, but it would take radar pictures, microwave pictures. So Mercury has these places where clearly at some point it kind of wrinkled up a bit. When you look at these kinds of photos, and anytime you're looking at photos of craters and things like that, one thing you always pay attention, you can always note right away. This crater is older than this scarp. How do I know that? Because it goes through it, right? The scarp's on top. If the crater happened afterwards, it would have erased that part of the scarp. Okay? It would have blown that part away. There is one large crater basin on Mercury, and by large we mean really large, 1,300 kilometers, which is 1,300 kilometers, probably like, it's almost 1,000 miles, right? So that is a long way. Odd radial cracks near the center, so this whole area is kind of depressed because of a large, very large impact at some point in Mercury's history. On the other side, opposite to this, there's very chaotic terrain, and it may be that this was caused by the impact, right? That the impact hit and sent shock waves around to the other side and caused the other side to kind of jumble up and be shaken up because of the impact. Here's the bad news about Mercury if you want to go there. Daytime, 820 degrees Fahrenheit. My oven only goes to 500. So, that's hot, right? Nighttime, minus 320 degrees Fahrenheit. So, you're either burned to a crisp or really, really cold, unless you go to the poles. Because at the poles, you can get at an angle where you get just enough sunlight to kind of keep you at a nice temperature, right? But only at the poles. The rest of the time, Mercury is so close to the sun, and because it has no atmosphere, if it's in direct sunlight, it's getting really hot, and if it's in shadow, it's getting really cold because there's no atmosphere to hold in the heat. And also, because of its mass, it doesn't have any atmosphere. And if it had a little bit of atmosphere, the sun would heat up the atmosphere quickly to the point where all the gas reached escape velocity from Mercury and went away. So if Mercury ever had any chance of having an atmosphere, its closeness to the sun keeps that from happening. All right. Mercury, little different from the other rocky planets. If you remember the pictures of like the moon where there's a small iron core and the Earth where there's an iron core, and all the inner planets have some sort of nickel iron core. Mercury's nickel iron core is large compared to the overall size of the body. And it may be, there are a couple of reasons this may be. One is that the stuff that makes up our mantle, and the stuff that makes up the mantle of Venus, the stuff that makes up the mantle of Mars, may have been too hot that close to the sun to actually condense and end up being part of Mercury. The other is, Mercury may have been hit by something pretty large at some point that blew away most of that material from Mercury. Will we ever know exactly which one of these two it is? Probably not. Right? But we form these hypotheses and we say it could be this, it could be that, and then we look for ways to test that. Right? The large impact hypothesis would have had Mercury be much more like the others with a relatively smaller iron core, and then the large impact drives away most of the silicate or rocky material on the outside, and what condenses back is just the iron core plus a little bit of silicate. You wouldn't be able to use a compass on Mercury, right? No magnetic field to speak of, in part because it's small molten core, and also because it doesn't really rotate much, right? So here's why when the sun is up it gets so hot. It would get really hot here in the sun if it took us 58 days to have a day, right? If the sunlight kept shining down for that long, if you're in the sun for half that period, right, 28, 25 plus 4, 29 days, almost 30 days. If you're in the sun that long, it's going to get hot. And then on the converse, when it's night that long, it's going to get really cold. And so we would have more extreme temperatures if this were the case for us. So, and also Mercury goes around the sun in every 87, 88 days. So there's a 2/3, 2 to 3 ratio between its day and its year. Right? Mercury barely gets in a day every year. It takes it so long to go around. This, if Mercury's orbit is more elliptical than ours, right? If Mercury's orbit was rounder and more centered on the sun, then Mercury would eventually slow down to where the same side faces the sun all the time. As it is, because it's elliptical, because its orbit's elliptical, it's going to keep rotating in this resonance, they call it, of 2/3. Venus. You guys have seen Venus a lot. In this picture we have the moon and we have Venus. Why do you always see Mercury and Venus around sunset and sunrise? Any ideas? Why are Mercury and Venus the things you see, the bright stars around sunset and sunrise? Where are Mercury and Venus with respect to us and the sun? They're between us and the sun. Right? And so, right? They're between us and the sun. So if the sun's over here, that means Mercury and Venus are going to be always on either side of the sun. Right? And so they're going to get farther from the sun, and then they're going to head back towards the sun, and they're going to head on the other side of the sun, and then head back. But they're always going to be, with respect to us, in the direction of the sun. That's why we see them at either sunset or sunrise. Venus is often very bright. Right? Venus is often very bright. So, the Newton atmosphere, mostly CO2, some nitrogen, and then there are small amounts of water in the atmosphere. And again, as I said earlier, the clouds, these clouds that make Venus so bright, sulfuric acid. We, because of that, we don't really ever get to see via telescope the surface of Venus. Occasionally we get a little glimpse. It looks kind of orangish, and it looks kind of orangish because the clouds absorb all the blue light, leaving just orangish light behind. The poles, which is the only place where it kind of cools off a little bit, is where a lot of the atmospheric action happens in terms of, it's almost like a permanent little tornado at the poles, where cold air is sinking, or cold atmosphere is sinking, and warm atmosphere is coming up from the pole and from the equator. So warm atmosphere comes up from the equator and sinks and goes back and warms up, and so we get this action going on at the poles. It's kind of like a drain, where the upper layer is sinking down, cooling and sinking down. Other thing about Venus is the atmospheric pressure is really high. Right? You get up to about 100 times what it is here on Earth. That's kind of like, if you think of our atmosphere as a blanket, right? Our atmosphere is more like a light sheet, and Venus's atmosphere is more like 5 or 6 heavy wool blankets, right? And because Venus's atmosphere is so thick, it gets hot. It gets hotter on Venus than it does on Mercury. Right? Mercury gets up to 800 something degrees Fahrenheit. Venus gets up to 900 degrees Fahrenheit because of those blankets. So the sunlight comes in and the heat from the sun comes in, but the atmosphere then holds it. Venus is one of those places where we began to understand the role of carbon dioxide in the planetary dynamics, right? You hear a lot about greenhouse gases and greenhouse warming and global climate change caused by CO2. It was Venus where we began to really understand what CO2 does in terms of letting heat in and not letting it out. All right? And so this is one of the issues we have on Earth, is we put more CO2 in the atmosphere, and as we've done that, we've begun to collect heat from the sun that we don't get to shed. And so that extra heat slowly builds up. Using radar, cloud penetrating radar, right? Venus is pretty flat. It's got some mountains, but not a lot. Compared to Earth, it's really flat. And, you know, if it weren't for the fact that it's 900 degrees and raining sulfuric acid, it might not be a bad place to go. Other things going on the surface, and one of the reasons it's so relatively flat is that Venus appears to be actively a volcanic. And so the radar picks up lava flows, and the radar picks up volcanoes, a lot of these that look pretty new. We didn't pick up any active volcanoes happening at the moment, but we have picked up a lot of signs of recent volcanoes. You know, get to see these little features. This is raw radar picture of a volcano where you can see the caldera at the top. I'm not sure what image processing they did for this, but the colors probably indicate different materials. So, young, active, things still going on. Surface of Venus only about 500 million years old, much younger than ours. Some regions less than 10 million years old. And we used to think of Venus as our twin, used to being a couple hundred years ago, because we could tell it was about the same size, right? So we thought it was our twin. But, you know, there's so much that's different that it's not really close to being Earth-like at all. We don't know of anything from Earth that could survive on Venus. We don't know of any way we could construct a shelter on Venus. It's just completely different. This is a picture from a Russian lander. You know, so we've landed some probes on Venus. They last for a little bit, and then they're done for, right? So we got back a few photos. All right. Much like Earth, this is where it is Earth-like. You know, there's a nickel iron core, and then there's good sizable silicate mantle, and then a crust of rocky material. But the water content on Venus is lower than on Earth, so it behaves differently. Venus rotates very slowly. So two things about Venus. We rotate at 23 degrees about like this, right? Venus rotates upside down. Right? So we go around the Earth, around the Sun like this, and we rotate in the same way. Venus goes around the Sun like this, but rotates in the opposite way. Venus also takes a long time to rotate, 243 days to rotate once. Why? Well, we don't know, but again, two hypotheses. One, something big hit Venus at one point in the past and knocked it all wonky. Right? The other is the tides between the Earth and the Sun have caused Venus to slowly, over the billions of years, change its rotation. So a solar day on Venus is 117 Earth days. It rotates too slowly to generate much of a magnetic field. So both Mercury and Venus rotate slow relative to us. If you look at Venus in its orbit, right? It goes from noon, it's rotating opposite to the direction of motion. And then halfway around it comes back to noon. This is why its day, right? Its day is 117 Earth days, but the time it takes for it to rotate all the way around is 243. Right? We're accustomed to, our day is so short relative to how long it takes us to go around the Sun, that the two don't have much to do with each other for us. But for Venus, look at this. By the time it gets back up here, where it's noon again, it's only rotated halfway around. Right? Its rotation is only halfway through. And it's not going to be back to this orientation where that is up until it's over here. All right? It's going to come back all the way around, and then it'll get over here, and finally be pointing in the same direction it was when we started. So that's why the number of days it takes to rotate is much longer than its actual day. Does that make sense? Everybody got that? No? Yes?
Say it one more time. Yeah.
So Venus takes, let's get the exact number. Okay. Venus takes 243 days to rotate around.
The sun.
No, to rotate.
Rotate.
243 days to rotate. Okay? 243 days. In the meantime, it's going around the sun. Right? So, by the time, if I'm Venus, in 172 days, 117 days, I've turned this way. Right? I've gotten that far around. And I've gotten back to where I'm facing the sun. So imagine the sun's here, and I'm rotating. Here's how we think about it. Because we rotate so quickly. Right? Here's the sun, I rotate in 24 hours. Oh, sun's, noon, noon, noon. And we do that 365 times. Right? Venus, rotating very slowly. So there's the sun, it's noon. One, I'm rotating backwards. Right? I'm doing it very slowly. And as I rotate around backwards, I eventually get to where, oh, there's the sun again. And it's noon again. But I'm now only halfway around. Right? I haven't rotated all the way around back to here.
Oh.
So, a year on Venus is shorter than a day?
Yes.
Okay.
A year on Venus, well, actually a year on Venus is shorter than the amount of time it takes it to rotate all the way around, but longer than a day. If we define a day as when the sun is at noon to when the sun is at noon, a day is 117 Earth days. Okay? But we haven't gone all the way through a rotation yet. Right? It's because by the time, from here with the sun facing the sun at noon to when I was rotated halfway around to here when I'm facing the sun at noon again, I haven't finished rotating around, but I've had a day. And part of that's because I'm turning opposite to the direction of motion. Right? If I was turning that slow with the direction of motion, it would take me longer to get back to noon. Right? So Mercury and Venus both do this because their days, their rotational period is so long compared to their orbital period. Okay, Mars. Mars is in the news again lately. Why?
Water.
Water. That's right, water. All right. Half the mass of Earth, half the radius, tenth the mass. Mostly the most Earth-like planet. Why? Because it has an atmosphere that doesn't necessarily kill us right away. Because it has water. Even before we discovered water in different places, we knew there was a history of water, and we knew there was some water in the ice caps. It's also why we've sent a lot of probes there. During the day, it's not bad. I mean, 50 degrees. That's not too bad. At night, it can get kind of cold. But during the day, not bad.
What's kind of cold?
What's kind of cold? Let's see if we have the number here. We don't have the number here. I think the number is something like minus 30. Yeah. I'm not positive. Yeah. So Mars also has this enormous canyon in it. This canyon, the Grand Canyon would be this like little squiggle in this. This canyon is longer than the United States is wide. And it is, 100 kilometers wide, so 60 miles wide, and 7 kilometers, or about 5 miles deep. Right? So the Grand Canyon would be just a little squiggle inside of this thing. We believe it was caused by the same eruption that created Olympus Mons. Right? Olympus Mons is named after what? Mount Olympus, right? Like so many things we see in the sky, named after Greek gods and Roman gods. Olympus Mons. Olympus Mons is kind of big. It's kind of big. It sticks out of the Martian atmosphere. Right? So it sticks up above the atmosphere, which none of our mountains come anywhere close to doing. Part of that's the atmosphere is thinner, but part of it is Olympus Mons is enormous. Right? 25 kilometers high, 3 times higher than Mount Everest. And it's clearly volcanic, and it has signs that there were more than one volcano at one point in here, and this is just the latest. It is, relatively speaking, kind of flat. Right? So this is Olympus Mons, part of it anyway, that we can get on here, because this is Everest. Right? So, and Mauna Kea, I want to go there one day. Mauna Kea in Hawaii is taller than Everest, but starts lower, right? Because it starts down in the ocean and works its way up out of the water and up. Mars has a tilt close to what ours is. That means that it has seasons, very much like ours. And when it is summer, the polarized cap on the sun side, the end facing the sun, shrinks, and the one on the other end gets bigger. And then when it goes around and the sunlight then comes on the other polar cap, the opposite happens. All right? And the polar caps there are mostly dry ice, which is just solid CO2. So mostly CO2, some water, a lot less water than we have. There are deserts, there are sand dunes because Mars has an atmosphere with winds. A lot of the sand has iron oxide in it. We can see on Mars also evidence that there was once upon a time surface water. So we see on Mars a lot of erosion patterns that we associate with the flow of water. So we can see in the geography of Mars that once upon a time there was water.
I have a question about that. Caps. You know, it says they have a frozen layer of CO2, but the bulk of the frozen material is ordinary water. But one of the questions on our quiz.
Yeah, I changed the answer.
Oh, you did?
Yeah.
Okay.
I caught that. Or somebody brought that to my attention, I'll put it that way. Right? So you can see the evidence of water having once been plentiful on Mars, right? We see that kind of stuff all over the place on its surface, which has always made us much more curious, all right? You can see areas that look like, wow, this must have been a lake because, you know, lake beds tend to flatten out because of sediment. So a lot of things indicate, wow, something was going on. One of our landers took a close up, and you can see again erosion and sediment. There are clouds, there are winds. The atmosphere is mostly CO2, was sewn into. Atmospheric density is about 1% of ours. I was wrong, minus 30, minus 67. So it's cold at night. So 50 degrees to minus 67. It's like living in Siberia. Right. So now what water is left on Mars is locked up as ice in different places. The flow, or the latest evidence for water on Mars was not water flowing openly on the surface, but it was evidence of water seeping up and moving along within rocks. Just like Earth, water on Earth moves through the Earth in rocks, right? It was evidence that that was happening on Mars. Because it has winds and because it has dust, Mars also has little dust devils, right? This is a good photo of, you've seen them here, you see them here in the Delta all the time after they plow the fields, right? Has everybody seen dust devils here in the Delta? No? Yeah? You know, you've got hot air coming in, and it all comes in and swirls around and goes up, and you get this little trail of dust going up. So, no rain, because the atmosphere is too cold, but we do see fog form in valleys, and so we do see fog form, and then it will precipitate out. It makes its way to the poles, it forms part of the pole. We see morning frost, which is mostly, it's probably CO2, but it could be some water, right? We see, again, evidence of water having run openly on the surface at times in the past. So you can see where the stream would have been flowing through here. So one of the things about all of this is that this means once upon a time, Mars had a thicker atmosphere. And if we look at the erosion of the craters and date the craters, it looks like about 3 billion years ago, Mars made that transition to having less atmosphere and no longer having protection that gave, or the erosion that presented. So where we're going to look for water on Mars, where would we look? This photo tells us not what water is there, but what hydrogen is there. And remember, hydrogen, when we find it on the Earth, is usually bound up in water as H2O. Right? So this tells us that the best candidates for water are the poles and a few other places here and there on Mars, where we can see a lot of hydrogen. Okay, again, we don't know how or why Mars lost its atmosphere, but we can come up with ideas. One is, again, it got hit by something big that simply made most of its atmosphere evaporate off. The other is that because of its low gravity, and because as planets age, their volcanic activity generally slows down. Because of that, low volcanic activity stopped putting new gas in the atmosphere. And once that's stopped putting it in fast enough to replace everything that was lost to space. And once that happened, Mars started having a net loss of atmosphere. And so over a couple of billion years, the atmosphere would have thinned to the point where it is today. Inside of Mars is about the same. And it does have some tectonic activity. These are pictures of Mars's moons, Phobos and Deimos. They're not close together like this, but Phobos and Deimos. They are pretty close to Mars, and you can see they're pretty small. 20 kilometers, 12 miles long. So you can take their moons and put them between here Clarksdale without any problem, right? Not all that big. So calling them moons is sort of making them sound a little grander than they actually are. They're captured asteroids. Our whole history of life on Mars began with a mistake by an early astronomer, Giovanni Schiaparelli. He spent a lot of time looking at Mars, and he did what all of us tend to do when we see something we don't quite understand. We try and make it fit into something we do understand. And so he saw all these structures on Mars that he ended up calling channels, which we've translated as canals, but he ended up calling them channels. So he saw a interconnected web of what he believed pathways that some sort of creature was traveling along. And